Chapter 11.1 Permutations. Many mathematical problems require careful analysis of complex events. Permutations and combinations develop a systematic way of counting. These systematic counting methods allow the solving of complex counting problems that arise in many facets of life. A cell phone kiosk sells 3 different models of phones and offers 4 different cases. Draw a tree diagram that represents the different options if a customer buys a phone and a case. Lists all of the possibilities. So we have 3 different phones to choose from. So phone 1, phone 2, and phone 3. Then we have 4 different cases to choose from. So for each phone, we can choose case 1, case 2, case 3, or case 4, which gives us 4 different options for that phone and case combination. Then same for phone 2, we could have case 1, case 2, case 3, or case 4. And phone number 3, we can have case 1, case 2, case 3, or case 4. So in total, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have 12 different options. B, how many different options are there? We already answered that, 12 options. Is there another way to find the number of different options without having to list them all? So we have 12 options. Notice we have 3 phones to choose from and 4 cases. 3 phones times 4 cases gives us 12 options. So we can multiply the number of options of the first item, the phone, times the number of options for the second item, the case, to get the total number of options. This is called the fundamental counting principle. The fundamental counting principle determines the number of possible outcomes. If one task is performed in A ways, a second task in B ways, and a third task in C ways, then all 3 tasks can be arranged in A times B times C ways. For example, if a restaurant meal consists of 1 of 2 salad options, 1 of 3 entrees, and 1 of 4 desserts, how many possible meals can there be? Using the fundamental counting principle, we have 2 salads to choose from. Then we can choose from 3 entrees. And then we can choose from 4 desserts. Two times 3 is 6. 6 times 4 is 24. So we have 24 meal options. We could also do this with a tree diagram if we wanted. We have salad 1 and salad 2. From there, we can pick between 3 entrees, entree 1, entree 2, and entree 3, entree 1, entree 2, and entree 3. And then for each entree, we can pick from 4 desserts. So dessert 1, dessert 2, dessert 3, dessert 4. Same with entree 2, dessert 1, dessert 2, dessert 3, dessert 4. And entree 3 as well, dessert 1, dessert 2, dessert 3, dessert 4. And then same for our second salad option, dessert 1, 2, 3, and 4 for entree 1. Dessert 1, 2, 3, and 4 for entree 2. And dessert 1, 2, 3, and 4 for entree 3. And then to count the total number of options, we just count the branches at the last step. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24 options. Example, how many ways can you rearrange the letters in the word math with no restrictions? So math has 4 different letters. So we have no repeating letters. There are 4 spots that we want to fill. 1, 2, 3, and 4. For the first letter, we can choose from any of the 4 letters. So we have 4 options for the first location. For the second location, we only have 3 letters left to choose from because we already used one for the first spot. And then for the third location, we have 2 remaining letters, and for the last location, we have 1 remaining letter. So fundamental counting principle, multiply 4 times 3 times 2 times 1. 4 times 3 is 12. 12 times 2 is 24. So there are 24 different arrangements of the letters M, A, T, H. Another way to say different arrangements would be to use the word unique. Part B, if each arrangement must begin with a vowel. So a vowel A, E, I, O, U, and Y, we only have one vowel here, which is the letter A. So if we have to begin with a vowel, then in our 4 locations, the first letter has to be A. There's only one A in the word math, so there's only one option. Then for the second option, we have 3 remaining letters to choose from. For the third option, we have 2 remaining letters to choose from. And for the last option, we have 1 remaining letter. 1 times 3 is 3. 3 times 2 is 6. 6 times 1 is 6. So we have 6 unique or different arrangements starting with a vowel. How many different ways can a teacher seat 4 girls and 3 boys in a row of 7 if a boy has to be seated at each end of the row? So we've got a row of 7, so let's draw 7 spots. 1, 2, 3, 4, 5, 6, and 7. We have 4 girls and 3 boys, and we know that a boy is going to be at each end of the row, so the front of the row and the back of the row. So I'm going to start at the front of the row. There are 3 boys to choose from for the first location that a boy needs to go, which is at the beginning of the row. Then at the back of the row, I also need a boy, but there's only 2 remaining boys to choose from. For the rest of the row, we don't have any restrictions, so we just look at how many students are left to seat. We have 4 girls, and we would have 1 remaining boy because we've seated 2 of the 3 boys. So we have a total of 5 students. So we would have 5 for the first spot, then we can choose from 4 students for the next spot, then we can choose from 3 students for the next spot, then 2 students, and then there's 1 student remaining. Using the fundamental counting principle, we multiply these together. I'm going to use my calculator for this one. 3 times 5 times 4 times 3 times 2 times 1 times 2. And we get 720. So there are 720 ways to seat the students with a boy at each end of the row. Example, how many 3-digit numbers can you make using the digits 1, 2, 3, 4, and 5 if repetition of digits is not allowed? We want a 3-digit number, so we have 3 spots to fill, 1, 2, and 3. We have 1, 2, 3, 4, 5 numbers to choose from for the first spot. Repetition is not allowed, so we can choose from 4 for the second spot since we've already used 1 digit, and then 3 for the third spot. Then multiply those together. 5 times 4 times 3 gives us 60. We get 60 different 3-digit numbers. How many 3-digit numbers can you make using the digits 1, 2, 3, 4, and 5 if repetition of digits is allowed? So we still have a 3-digit number, so 3 spots to fill. We have 5 numbers to choose from. Then for the second digit, we still have 5 to choose from because we are allowed to reuse the number we've already used. So again, for the third spot, we have 5 numbers to choose from. That gives us 5 times 5 times 5, which gives us 125 different 3-digit numbers. Notice that when repetition is allowed, we get a larger number of options than when repetition is not allowed, which makes sense since we can reuse numbers. Factorial notation. Factorial notation is an abbreviation for products of successive positive integers. For any positive integer n, the product of all the positive integers up to and including n is n factorial. Factorial is shown with an exclamation point. N factorial equals n times n minus 1 times n minus 2 times n minus 3, so on, until we get to 3 times 2 times 1. And n has to be a natural number, so a counting number. Note, 0 factorial is defined as being equal to 1. 5 factorial is pronounced 5 factorial, and we write it as 5 factorial equals 5 times 4 times 3 times 2 times 1, which equals 120. To get factorial in your calculator, in a TI, if we were doing 5 factorial, you would push 5, then the math button, then the left arrow, and then number 4 should be the factorial. In a Casio, if you're doing 5 factorial, you'd push 5, then option, then F6, then F3, which is probability, and then F1 will be your factorial button. Hit EXE, and you get 120. Example: an online shopping website requires users to set up a password consisting of 6 letters. Hackers try to access the site by guessing the password, but it is not enough to know the letters, they must enter them in the correct order. How many 6-letter passwords can be formed if the letters cannot be repeated? We have 6-letter passwords, so 1, 2, 3, 4, 5, and 6. We're choosing letters from the alphabet. There are 26 letters in the alphabet, so for the first spot we have 26 letters to choose from. Letters cannot be repeated, so for the second spot we only have 25 letters to choose from. Then 24 letters, then 23 letters, then 22 letters, and then 21 letters. We calculate this. Notice this is not 26 factorial because we don't continue going times 20 times 19 times 18 all the way down to 1. It's just the first 6. 26 times 25 times 24 times 23 times 22 times 21. So just put that in your calculator. 26 times 25 times 24 times 23 times 22 times 21 and hit equals. We get 165,765,600 different passwords. Permutations. A permutation is an arrangement of a set of items in which the order of the items is important. The notation NPR is used to represent the number of permutations or arrangements in a definite order of R items taken from a set of N distinct items. Another way to write this is P bracket N comma R. But more commonly, you'll see NPR like this. The formula for a permutation is N factorial divided by N minus R in brackets factorial. And note that N has to be greater than or equal to R, and R has to be greater than or equal to 0. N is the number of items we have to choose from. R is the number of items we are choosing. We have to choose a smaller or equal number of items as the number of items that we have to choose from. So that's why R has to be smaller than or equal to N. So for the password example, we get that N is 26 because we have 26 letters to choose from, and R is 6 because our passwords have to be 6 letters long. So this would be written as P bracket 26 comma 6 or 26 as a subscript, P and then 6 as a subscript, which equals N factorial, which is 26 factorial, over N minus R, so 26 minus 6 in brackets factorial, which equals 26 factorial over 26 minus 6 is 20 factorial. And then algebraically, we can write this as 26 times 25 times 24 times 23 times 22 times 21 times 20 factorial over 20 factorial. I can do this because the definition of factorial means start with the number, then multiply it by one less, one less, one less, one less, etc. until you get to 3 times 2 times 1. So I could write this as 26 times 25 times 24 times 23 times 22 times 21, and then times 20 factorial. I don't have to write all the numbers out. I can stop here. Why am I stopping there? Because I have 20 factorial on the bottom, so now I can divide out those factors. Divide this one out, divide this one out. I'm now back to 26 times 25 times 24 times 23 times 22 times 21, like I had on the previous page. So we can enter this in our calculator in two different ways. We could do it algebraically, as I did, and show that it's equal to 26 times 25 times 24 times 23 times 22 times 21, and put that in our calculator like we did on the last page. Or we can use the permutation button in the calculator. So in a TI for 26P6, you would do 26, then the math button, then the left arrow, then option number 2 to choose permutation, and then put the 6 in for the R value, then equals. For 26P6 in a Casio, you put 26, then push option, then F6, then F3, then F2 for permutation, and then put the 6 in for the R. And any way that we do it, we should still get 165,765,600. Example, evaluate 7P2 algebraically. So N equals 7 and R equals 2. The formula for NPR is N factorial over N minus R factorial. So for 7P2, that would be 7 factorial over 7 minus 2 factorial, which equals 7 factorial over 7 minus 2 is 5 factorial. We want to evaluate this algebraically. We can rewrite 7 factorial as 7 times 6 and then times 5 factorial. I stop there because I have 5 factorial on the bottom, so I want to be able to divide those out. And then I just get that it's equal to 7 times 6, which is 42. Example, show that 5 factorial minus 3 factorial equals 19 times 3 factorial. Let's write 5 factorial as 5 times 4 times 3 factorial, then minus 3 factorial. So I've just taken the first term and rewritten it as this. And the reason I did that was so that I had a 3 factorial in each of the terms on the left side. That's equal to the right side, which is 19 times 3 factorial. Then I can factor out 3 factorial from this side because 3 factorial is in both terms. So I get 3 factorial times 5 times 4 and then minus 1. 3 factorial divided by 3 factorial would be 1 equals the right side, 19 times 3 factorial. And then simplify the left side, 3 factorial times 5 times 4 is 20 minus 1. Right side is 19 times 3 factorial. And then 3 factorial times 20 minus 1 is 19 equals 19 times 3 factorial. So left side is equal to the right side. Therefore, we have shown that 5 factorial minus 3 factorial is equal to 19 times 3 factorial. Solve for n if np2 equals 56. We're trying to figure out what n is. We know that r is 2. The formula for np2 is n factorial over n minus 2 in brackets factorial. We know that this equals to 56. It says right here, this equals 56. So I can replace the np2 on the left with 56 equals n factorial over n minus 2 factorial. Then I want to rewrite n factorial as a product that has n minus 2 factorial so that I can divide out this factor. 56 equals n times n minus 1 times n minus 2 factorial, right? Because n factorial means n times 1 less than n, which is n minus 1, times 1 less than that, which is n minus 2, etc. So I can write that as n times n minus 1 times n minus 2 factorial over n minus 2 factorial. Now I can divide out the n minus 2 factorial, that's a factor on top and bottom, and I'm left with 56 equals n times n minus 1. Then I can multiply the n into the brackets, and I get 56 equals n squared minus n. And now since I have a variable squared, I likely want to move everything to one side and see if I can factor the trinomial. So minus 56 on both sides. We get 0 equals n squared minus n minus 56. We want two numbers that multiply to negative 56, and they need to add to negative 1. That would be negative 8 and positive 7. Negative 8 times 7 is negative 56. Negative 8 plus 7 is negative 1. So we get 0 equals n minus 8 times n plus 7. Then solve for n. N minus 8 equals 0 when n equals positive 8, and n plus 7 equals 0 when n equals negative 7. We know that n in the permutation has to be a natural number, which does not include negatives. So n equals negative 7 is out. N has to be an element of the natural numbers, and n is not an element of the natural numbers for negative 7, which means that n equals 8 is our solution. And n equals 8 is an element of the natural numbers. Example, motorcycle license plates consist of 2 different letters followed by 4 different digits. How many different plates are possible? So we have 2 different letters. That means we're not repeating. Followed by 4 different digits. So again, not repeating. There are 26 letters in the alphabet, and there are 10 digits. 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So we've got 2 letters to start, 1, 2, and then we have 4 digits, 1, 2, 3, 4. For the 2 letters, the first letter we have 26 options. We're not repeating, so the second letter is 25 options. Then for the digits, We have 10 options for the first digit. We're not repeating, so we have 9 options for the second digit, 8 options for the third digit, and 7 options for the fourth digit. We can calculate that by doing 26 times 25 times 10 times 9 times 8 times 7 in our calculator, and we get 3,276,000 different plates. Another way to calculate that is we can do 26 P2 times 10 P4. Since we are choosing 2 of the 26 letters and 4 out of 10 digits. So we can put it in that way in our calculator. If we do that, 26 P2 times 10 P4, and again I get 3,276,000. You should try it both ways, make sure that you get the same number. Peter did not study for his math test. He must answer 10 multiple choice questions with 4 choices each. If he guesses on each question, then in how many different ways can he record his answers? There are 10 questions to answer, and each question has 4 choices. So we can write this as 10 options. And then for each of those, we have 4 answers to choose from. So it would be 4 every time. And we would multiply those together. So you could enter that into your calculator the way it is, or an easier way, this would be 4 to the power of 10. Enter that into your calculator, and you will get 1,048,576 different ways to record his answers. But he should probably just try studying. That would be helpful. Example, how many 4-digit numbers can be formed if Part A, only the digits 1, 2, 3, 4, and 5 are used, and if no repetition of digits is allowed. So we have a 4-digit number that we're creating. We have 5 digits to choose from, 1, 2, 3, 4, and 5. So we can do 5 options for the first digit. Then there's no repetition, so we have 4 options for the next, 3 options for the next, and 2 options for the last. Multiply those together, and we get 120 different 4-digit numbers. Another way we could do this is using permutations. So we have 5 digits to choose from, and we are choosing 4 of them. Put that in your calculator, 5P4. And again, you should get 120. Part B, any digit can be used, but not repeated. So we're still making a 4-digit number. Any digit can be used. There are 10 digits, but when we're making a number with a certain number of digits, the first digit cannot be 0. The reason is then it's really a 3-digit number. If you start with 0, that's like starting without a digit. So then it becomes a 3-digit number. So it can't be 0, or it becomes a 3-digit number. So if we exclude 0 from the first location, then we have 9 digits that we can use. Then for the second spot, we would have 9 again, because now we can use 0. So there was 8 that we didn't use in the first spot, and also 0 that we can now use. So there's a total of 9 digits. Then we would have 8 digits that we could use, and then 7 digits. Calculate this. 9 times 9 times 8 times 7 gives us 4,536. Different 4-digit numbers. And if we wanted to use permutations, we could write this as 9 times 9p3. For this part, we are choosing 3 digits out of 9, because we've already used one here, so now we have 9 remaining, and we're choosing 3 of them. So we have 9 times 9p3. Put that in your calculator. 9 times 9p3. We should get the same thing. Yes, we do. 4,536. And then part C, any digit can be used and can be repeated. So we are allowed repetition here. Again, any digit can be used. We still need to make it a 4-digit number. So again, we cannot start with 0 or it becomes a 3-digit number. So that means we have 9 digits to choose from for the first location. But then since we're allowed repetition, we can choose any of the 10 digits for the other 3 locations. So 9 times 10 times 10 times 10. And that gives us 9,000 different 4-digit numbers. Permutations with repeating objects. How many different arrangements can be made using the letters of the word mo? A, list all the possible arrangements. So let's say we start with M. We could have M, then O, then W, or we could have M and then W and then O. So there's 2 different arrangements. If we start with O, we could have O, then M, then W, or we could have O, then W, then M. And if we start with W, we could have W, then O, then M, or we could have W and then M and then O. So we get 2, 4, 6 different arrangements. Another way to show this is using the fundamental counting principle or permutations. We have 3 letters to choose from, 3 times 2 letters remaining to choose from, and then times the last letter remaining. 3 times 2 times 1 is 6 arrangements. And this should be the same as choosing 3 from 3. So 3p3, if you do that in your calculator, 3p3, you get 6. B, now change every W to an O to list all of the arrangements of the letters of the word moo. So in the word moo, we have 2 O's. I'm going to call that O1 and O2. So if we start with M, we have M, O1, and then O2, or we could have M, O2, and then O1. But really, these are the same. We want to know how many different arrangements we have, but MOO is the same as MOO. Doesn't matter that we have two O's. They're the same. Then we could put M in the middle, so we could have O1, M, O2, or O2, M, O1. But those, again, are the same. OMO is the same as OMO. And if we put M at the end, we could have O1, O2, M, or O2, O1, M. And again, those are the same. Two O's and then an M. So how many different arrangements we have? We have 3 different arrangements. Which are MOO, OMO, and OOM. Part C, express both answers from A and B in factorial notation. For part A, we had 3 times 2 times 1, which is 3 factorial. For part B, when we have repetition, what we do is we divide it out. So we started with 3 times 2 times 1, but then what we did was divided by the repetition, which is 2 times 1, because there's 2 O's, so 2 factorial. So this gives us 3 factorial over 2 factorial. Since there are 2 O's, that's 2 factorial, so we divide out the repetition. A set of n objects with A of one kind that are identical, B of another kind that are identical, and C of another kind that are identical, etc., can be arranged in n factorial divided by A factorial times B factorial times C factorial different ways. When items repeat, we must divide out the duplicates. How many unique arrangements of the letters of the word Mississippi are possible? Let's count the total number of letters we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 letters total. But we also have repeating letters. We have repeating I's. We've got 1, 2, 3, 4 I's. We also have S's repeating, 1, 2, 3, 4 S's. And we have P's repeating, we have 2 P's. So for the unique arrangements, we need to divide out the repetition like we did on the last page. So we have 11 factorial, the total number of letters, divided by the repetition, 4 factorial for I's, 4 factorial for S's, and 2 factorial for P's. Then we can calculate this in your calculator. Do fraction button if you have that. 11 factorial over 4 factorial times 4 factorial times 2 factorial Calculate that, and we get 34,650. Unique arrangements. How many different 5-digit numbers can you make by arranging the digits of 17171? Again, we want different arrangements, so we're going to have to divide out the repetition. We have a total of 5 digits. But there are 3 ones and 2 sevens. So our different arrangements would be 5 factorial over 3 factorial times 2 factorial. Put that in the calculator. Five factorial over 3 factorial times 2 factorial. Enter, and that gives us 10. 10 different arrangements. In how many different ways can you walk from A to B in a 3x5 rectangular grid if you must move only down and to the right? A couple different ways that we can do this. We can use the grid to figure it out, or we can divide out repetition as we were doing above. Let's use the grid first. I want to look at how many ways there are to get to each intersection point. So here's an intersection, here's an intersection, here's an intersection, etc. Any intersection of 2 lines. So to get here, there's one way. I go directly to the right from A. There's also one way to get here because I go directly to the right from A. So there's only one way to go. And same with all the way along here. There's only one way to get to each of these intersection points because I can only go directly to the right. Same with going down. I can only go directly down to get here, or here, or here. So there is one way to get to each of those intersections. Then to get here, I can either go right and then down, or I can go down and then right. So there's 2 ways to get to this intersection point. To get to this intersection point, I can go right and then down, or I can go right, down, and right, or I can go down and then right. So there's 3 ways to get to this intersection point. To get to this one, I could go right and then down, right, down, right, or right 1, down 1, right 2, or down 1 and right 3. So I have 4 ways to get there. Are you noticing the pattern? The sum of the diagonals equals this one here. So 1 plus 1 is 2. 2 plus 1 is 3. 3 plus 1 is 4. Next one will be 4 plus 1 will be 5. And then 5 plus 1 will give us 6. And so on. 1 and 2 is 3. 3 and 3 is 6. 6 and 4 is 10. 10 and 5 is 15. 15 and 6 is 21. 1 and 3 is 4. 4 and 6 is 10. 10 and 10 is 20. 20 and 15 is 35. And 35 and 21 gives us 56. So there are 56 ways to get from A to B if we're only allowed to move down and right. Now the other way that we can do this is like we did above with factorials and dividing out repetition. We have 1, 2, 3, 4, 5 moves to the right. And 1, 2, 3 moves down. That gives us a total of 8 moves. But 5 of those moves are going right, which is the same repetition, moving to the right. And 3 of those moves are going down, which again would be repetition. So then factorial form, we get 8 factorial over 5 factorial times 3 factorial. And then we calculate that. 8 factorial over 5 factorial times 3 factorial gives us 56. 56 ways from A to B if only moving down and right. Permutations with restrictions. Using all the letters in the word Columbia, determine the number of possible arrangements if there are no restrictions. So in the word Columbia, we have 1, 2, 3, 4, 5, 6, 7, 8. 8 letters. There's no repeating letters. And we want to know if there's no restrictions. That would be 8 factorial, or 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Calculate that. 8 factorial gives us 40,320 arrangements. Part B, if the first letter must be an L. So we have 8 letters, 1, 2, 3, 4, 5, 6, 7, and 8. The first letter has to be an L. That means we're choosing one of the letters. There's only one L. Then we have 7 remaining letters, then 6, then 5, then 4, then 3, then 2, and then 1. Multiply those together. We can also write this as 1 times 7 factorial, or just 7 factorial. So in our calculators, 7 factorial gives us 5,040 arrangements. Part C, the last 2 letters must be vowels. So we have 8 letters, 1, 2, 3, 4, 5, 6, 7, and 8. The last two letters have to be vowels. How many vowels do we have in the word Columbia? A, E, I, O, and U. So we have A, I, O, and U. We have 4 vowels. So the last two letters, we would have 4 to choose from because we have 4 vowels to choose from, and then we would have 3 to choose from because there's 3 remaining vowels. Then for the other letters, there would be 6 remaining letters. So 6 times 5 times 4 times 3 times 2 times 1. We could also write this as 6 factorial times 4 times 3, and then calculate 6 factorial times 4 times 3 is 8,640 arrangements. Let's just put a note here. These are the vowels. Ends with 2 vowels. And then this here is for the 6 remaining letters. Part D, the letters O and M must be adjacent or together. Notice there's 2 ways that we can put O and M together. We could have O-M or we could have M-O. In this case, or in cases like this, what we do is we consider those 2 things that must be together as one item. So consider O and M as one letter. Then we have 7 letters to arrange. So instead of 8 letters, we now have 7. 1, 2, 3, 4, 5, 6, 7. Then we have 7 times 6 times 5 times 4 times 3 times 2 times 1. But that is with one variation of O and M. We then times that by 2 because we have 2 options for O and M. We could have O and then M, or we could have M and then O. You can also say that we're timesing it by 2 factorial. If we had 3 letters together, we would times it by 3 factorial. 3 times 2 times 1, because the way you arrange the letters that have to be together would be the number of letters you can choose from first, which would be 3, then 2, then 1. In this case, we have 2, so we're choosing one of 2 letters, and then we have 1 letter remaining, 2 times 1. So this can also be written as 7 factorial times 2 factorial, but 2 factorial is just 2 times 1, which is 2, so 7 factorial times 2. Plug that into our calculator. 7 factorial times 2, or 2 factorial, gives us 10,080 arrangements with O and M together. Part E, the letters O and M must not be adjacent or must not be together, so they have to be separated. For these types of questions, we take the total arrangements and we subtract the arrangements with O and M together, which we calculated in part D. So our total arrangements with no restrictions was from part A, which was 40,320, minus the arrangements with O and M together, which we calculated in the last part, 10,080. Calculate that, 40,320 minus 10,080 gives us 30,240. Arrangements with O and M not together. Arrangements requiring cases. When there are different cases to deal with, you must count the different arrangements. Some problems have more than one case, so count the number of arrangements for each case and then add the values for all cases to obtain the total number of arrangements. Example, how many 4-digit odd numbers can you make using the digits 1 to 7 if the numbers must be less than 6,000 and no digits are repeated? The numbers 1 to 7, let's write those out. We have 1, 2, 3, 4, 5, 6, and 7. We're talking about odd numbers, so let's distinguish between odd and even. The even numbers are 2, 4, and 6. And the odd ones are 1, 3, 5, and 7. We want a 4-digit number. It needs to be an odd number, and it needs to be less than 6,000. If it's less than 6,000, it's going to need to start with a digit that is less than or equal to 5, because if it starts with 6 and then is followed by any of our other numbers, it'll be bigger than 6,000. If it starts with 7, obviously it's bigger than 6,000. So we're going to have two cases here. Case number 1 is an even first digit. So we've got 1, 2, 3, 4-digit number. The first number is going to be even, which is 2 or 4, because our even numbers are 2, 4, and 6, but our number has to be smaller than 6,000, so I can't pick 6 for my first digit, so 2 or 4 is what I have to choose from, which gives me 2 options. My last digit has to be odd, because this is an odd 4-digit number, so the last number has to be odd to make the 4-digit number odd. So I can choose from 1, 3, 5, or 7, which means I have 4 numbers to choose from. The 2 remaining numbers, we don't need to restrict, so we just look at how many numbers do we have left from our 1 to 7. We have used 2 of them, so we had 7 digits. 1, 2, 3, 4, 5, 6, 7. We've used 2 of those, so we now have 5 remaining. So we have 5 to choose from for this spot, and then 4 to choose from for this spot. Then 2 times 5 times 4 times 4 and we get 160. 4-digit odd numbers starting with an even number or digit. That's our first case. Our second case is if we have an odd first digit. We still are making a 4-digit number. This time we're putting an odd at the beginning and also an odd at the end. In the beginning, we can only choose odd numbers that are smaller than 6. So 1, 3, and 5, which gives us 3 options. Then for our last digit, we can use any of the odd numbers. So this would be the odd numbers remaining. Which would be 3 because we have a total of 4, but we used 1 for the first digit, so there's 3 left. And then again with the middle 2, we just look at how many digits we have remaining. There is a total of 7, 1 to 7. We've used 2 of them, 1 for the first, 1 for the last. So we have 5 remaining, and then 4. So 3 times 5 times 4 times 3. Which gives us 180 4-digit odd numbers starting with an odd digit. Then we do the total. Total is 160 plus 180, so add the numbers from each case. 160 plus 180 gives us 340 4-digit odd numbers less than 6,000. I guess I could add that up here as well. 4-digit odd numbers less than 6,000, starting with an odd digit, and 164-digit odd numbers less than 6,000, starting with an even digit. That brings us to the end of Chapter 11, Lesson 1, Permutations.